Hello everyone. In this lecture, we are going to learn the concept of constraint motion and then we are going to solve few problems related to the concept. So let's get started. So today we are going to discuss about constraint motion. Now here the term constraint basically means restriction. So clearly we can define constraint motion as a restricted motion. We can say that if the motion of a body is restricted in some way, then we can say that it is a constraint motion. Now, for example, let's say a train moving on a railway track. So here the motion of the train is always constrained or restricted to the path of the railway track. So we can say that the motion of the train is a constraint motion. Another example would be a car moving on a one-way road. Here also the car cannot go off the road, so it will follow the path of the road and hence it is restricted or constraint motion. So let me take another example. Let's say I have a wedge like this, and if I place a block on my wedge and if I leave the system like this, naturally the block will move down following the path of the wedge, right? So here while moving down or while sliding down, the block will follow the path of the inclined plane AB, right? So the motion of the block is restricted to the path AB, and hence we can say that it is a restricted motion or constraint motion. So let's take the final example. Let's say I have a single fixed pulley with two masses suspended on either side, mass let's say M1 and M2. Now if I pull down the mass M1 by let's say some distance, then the mass M2 will move up, and if I pull down the mass M2, then mass M1 will move up. So we can say that the motion of one mass or the motion of one block is completely dependent on the motion of the other block. So this is also an example of constraint motion. Now let's dive into the three types of constraint motion that we have. Three types of constraint motion. The first one is string constraint, which basically says that for an inextensible string, the length of the string is constant. the string is constant. So to explain this, let me take an example. Let's say I have two blocks connected with a string. So this is block A connected with a string. We have block B, and let's say the initial length of the string is L0, and if I displace the block B by a distance xb towards right, the final position of the block B will be somewhere here, and as a result of that, block A will also get displaced. Let's say the displacement of block A is xa for now. Let's say this distance is xa. So you have to calculate the final length of the string. The final length of the string, that is LF. So we know that initial length is L0, and you have to calculate the final length. Final length will be initial length, that is L0, plus the extension due to the displacement of block B, that is xb, minus the contraction due to the displacement of block A, that is xa. Right? So now the extension in the string will be final length minus initial length, that is L0 plus xb minus xa, plus xb minus xa, minus the initial length L0, that will be xb minus xa. Now we know that for an inextensible string, we can write for an inextensible string, the extension is 0. So xb minus xa will be 0, or we can say that xb is equal to xa. So which means that if I displace the block A by some distance, let's say this was a block A. So if I displace the block A by some distance in this direction, xa, so the block B will get displaced in the same direction by the same amount. So this will also be xa. In the same way, if I displace the block B in this direction, xb, the block A will also get displaced in the same direction by the same amount. So from this relation we can say that, so let's say this relation is x1. From this relation we can say that if I differentiate this relation with respect to time, so we will get dxb by dt is equal to dxa by dt, or vb is equal to va. That is, velocity of B will be equal to velocity of A. So if this block B moves in this direction with a velocity Vb, the velocity of the block A will be in the same direction and the same magnitude. So we can write here as vectors. So from this, if I again differentiate it, we will get acceleration of, let's say acceleration is f, let's say fb will be equal to fa. So acceleration of b will be equal to acceleration of a from this relation. So these are the three relations that we got. To sum this up, we can say that the relative motion along the length of the string will be 0. Now the relative motion of the two blocks along the length of the string will be 0. Now that means if this block moves by a velocity v towards right, let's say this block will also move in the same direction with the same velocity. That means the relative velocity, if I calculate Vv minus Va, that will be 0. So same goes for acceleration, same goes for displacement. So the next type of constraint motion that we have is pulley constraint. So let me take an example. Let's say I have a system of pulleys like this. Let's say this has mass m1, this has mass m2, and suppose the velocity of mass m1 is v in the downward direction. So you have to calculate what is the velocity of mass m2, right? We usually get this kind of problem in pulley constraint. So to solve this, we have three constraint relations. Let me write it down. The first one is summation of T dot x is 0. Here T is the tension, x is the displacement. So both are vector quantities. Next we have summation of T dot V equals 0. And the third, summation of T dot A is equal to 0. The second and the third one can be derived from the first by simply differentiating with respect to time. So the main concept behind the first one, the first relation, is the concept behind the first relation is based on the fact that the work done by internal forces in a rigid system is 0. So let us now solve this problem. So before solving, let us assume that the mass m2, the second mass, is moving with a velocity v2, and we don't know what the direction is. So let's assume that for now that the velocity is v2 in the upward direction. Now let's mark the tension in the strings. We have only one string in the system, so the tension will be same everywhere. Now we can apply the second relation that we have, summation of T dot V is equal 0. So we can write, for the first mass, the tension is T, the velocity is V, so T dot V will be TV cos 180 degree, so negative. For the second mass, the total tension acting on the second mass is 2T, and the velocity is V2, so dot V2, right? And the angle between 2T, the T vector and the V vector is same, V2 vector is same, so cos 0, which is 1. So we get, for the second mass, we get 2T into V2, that will be 0. So V2 is equal to, we get V by 2. The third and the final type of constraint motion that we have is wedge constraint. So in wedge constraint, if two bodies move in a way such that they always keep contact with each other, then we can say that the relative motion of the two bodies along the normal to the plane of contact will be 0. Now this will be clear if we take an example. We'll see one in the problem. First problem says that two bodies of masses m1 and m2 are connected through a string as shown in the figure. Now if m2 is pulled with a velocity u along the ground, then find the velocity of m1. Right? So let us assume that the velocity of m1 is v. Okay, so mass m2 is pulled in this direction. So that means the mass m2 will pull the string in this direction, and the string is connected to m1. So the string will pull the mass m1 in this direction. So let's assume that the velocity of m1 is v in this direction. Okay, so the velocity of mass m1 is v in this direction. Right, now our system would be mass m1, string, and mass m2. So we can easily apply our constraint relation T dot v, summation of T dot v is equals 0. Now before that you have to mark the tensions. So the magnitude of the tension will be same. Right. Now simply for mass m1 the tension is T and velocity is v. Their angle between them is 0, so cos 0 is 1. Plus for second mass we can write the tension T and the velocity is u, and cos of the angle between tension and velocity u. So what will be the angle? The angle will be, this is theta given, this angle is theta given, so this angle will be 180 minus theta. Right, so we can write here 180 minus theta, this is equal to 0. Now cos of 180 minus theta is simply minus cos theta, so we can write minus tu cos theta equals to 0. So t will get cancelled out, so we are left with v is equals to u cos theta. So our next problem says that consider the above pulley block system and find the relation between the acceleration of the bodies. So first let us assume that the acceleration of mass m1 is a1, the acceleration of mass m2 is a2, and the acceleration of mass m3 is a3. Now we have to find the relation between a1, a2 and a3. Right, now we can assume the acceleration in any direction. I have assumed all of them in the downward direction. So let's mark the tensions now. We have one string throughout the system, so the tension will be same everywhere, T, 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 and here tension T. So now applying our constraint relation, now from here we will get, for the first mass m1 the tension is T, the acceleration is a1 but in the downward direction, so the angle between them is cos 180. Right, the angle is 180, so on dot product there will be cos 180, so negative. For the second mass m2, the total tension that is acting on m2 is 2t. Right, so for second mass the tension will be 2t, acceleration is again a2 but in the downward direction, so again cos 180 degree, so negative. For the third mass M3, the total tension acting on M3 is again 2T, right? And the acceleration in the downward direction A3, so their dot product will be minus 2T A3, and this sum will be 0. So from here we can easily get that A1 plus A2, sorry, plus 2A2 plus 2A3 is 0. Let's take our next problem, which says that a rod B of mass m is constrained to move along the walls of the wedge A of mass capital M. If wedge can freely slide on the ground, then find the relation between the acceleration of the rod and the wedge. So clearly the rod here is constrained to move in the vertical direction. So this wall is acting as a constraint, right? Now due to its weight, the block B or the rod B will move in the downward direction. Let's say the acceleration of block or the acceleration of the rod B is AB in the downward direction. Now as a result, the wedge will move in this direction with acceleration, let's say AA, right? So if I draw these things over here, I'll get acceleration of block B is this direction, acceleration of A of wedge A is in this direction. Now we know that throughout the motion the rod and the wedge will always be in contact, so we can apply our wedge constraint relation, that is along the normal their relative velocities, or here the relative accelerations along normal is 0, right? Let's draw the normal here. Right? If this angle is theta, so this angle will be theta. This angle is 90 minus theta, so this angle is theta, right? Now acceleration of rod B along normal would be, that is acceleration of rod B along normal would simply be AB cos theta, right? And acceleration of wedge A along normal would be AA sin theta, right? Now we know that relative acceleration along normal should be 0, because they will always stay in contact with each other. So we can write relative acceleration, that is acceleration of A with respect to B or B with respect to A along normal should be 0. So we can write acceleration of A with respect to normal minus acceleration of B along normal, that is 0, or we can simply equate them, right? And acceleration of A normal, this is our first equation, let's say this is our second equation. From second equation we can write acceleration of A along normal is AA sin theta, and acceleration of B along normal is AB cos theta, and this is equal to 0. So from here we can write AB is equal to AA tan theta, right? So this was all. Thank you.